Okay, good day. Part 5, people. So that last example, I had x squared plus 5x plus 6. I'll just prove that to you because I just took those 8s and put them on top of the 6s because I wanted to see how adding 2 to the polynomial dividend would change the way I could understand this whole thing. So there's stuff on the screen here that isn't correct yet. We've got to now fix it. We're going to do some fixing. So no longer is x squared plus 5x plus 8 equal to this. So to fix that, this I know equals 5x plus x squared plus 5x plus 6. So I'm going to have to add, well, maybe I'll do this in a totally different color so we really know we're in a different land. Something not very irritating. Green is definitely not irritating. Okay, so we have plus 2 there because if we had the plus 6 before and now we added 2, we have to add 2 to both sides of the equation. That makes sense. Okay, so now in this version here, what are we going to do? Now when we divided, we get this quotient. Oh, I know what we have to do now. We have to add 2, which has still yet to be divided by x plus 2. That's in that version of that division statement, right? That's the one Sarah asked about, and that's where we said 13 is equal to 3 1/4 because 13 divided by 4, oh no, 13 divided by 4 is equal to 3 1/4, right? Okay, and another way to understand is comparing these two. If I take this division statement and I divide everything by x plus 2 I get here. Divide this by x plus 2, I just get this piece. I divide this by x plus 2 and I just get this piece. So there's a second way to relate the two together algebraically. Okay, so now what's going on here with the long division? Well, here now I have to acknowledge that the subtraction is 2, so it's kind of not very different at all, especially with something so, with quite a short polynomial to start with. Okay, so now what's happening here? That's the polynomial, yeah, check. But now when I sub this in, what is this going to be? Well, let's take a look. First of all, I'll erase what's there because it's not good to have incorrect stuff. Okay, so now we get negative 2 squared is positive 4, negative 10, that gets me down to negative 6 plus 8, well, lo and behold, that's 2. And why do you suppose that happens? Because when I put, I'm just going to use a highlighter now, when I put that negative 2 into this version, because this is all the same stuff, right? If I put a negative 2 in here, that kills this guy. There's my skull and crossbones. It kills that factor. It doesn't matter what happens in this place here. Negative 2 plus 3 happens to be 1, but even if it didn't, this is 0 times whatever this is 0 plus 2 is all that can come out of this. It's a very strategic number to sub in, that negative 2. So we get this 2 out of the function evaluated at negative 2. Because our remainder happens to be 2. This is a coincidence. The 2's are coincidences in this case. The 2, 2, 2 isn't all the same, right? So these two 2's relate to one another, and these two 2's relate to one another, okay? And there we are. I find this quite compelling in proving how it is that the division theorem, the remainder theorem, and the factor theorem work. And I find this form of the division statement critical as I think about that. What is going to kill that multiplicative piece of this so that all I'm left with is the divisor? Well, it's going to be one of these two numbers with the additive inverse of one of these two numbers, either negative 2 or negative 3. Okay, people, I'm done for the day. That was part 5 of long division and the two theorems, remainder and factor theorem.